In this video, I'll discuss the power rule, perhaps the most well-known of all the derivative shortcuts. The power rule is very simple and efficient to use and will save you so much time so that you won't have to calculate derivatives using the limit definition any longer. Okay, maybe once or twice more as we learn a few more derivative rules. Here's the power rule. Say you have a function of x that looks like ax to the n, where a and n are real numbers. If you want to find its derivative, simply take the exponent n and multiply it by the coefficient of a to get n times a, and decrease the exponent by 1, n minus 1. That's it. That's all there is to it. The power rule tells us that the derivative of a fifth degree polynomial will be a fourth degree. A fourth degree will be a third degree, and so on down the road. We'll take a look at a proof to see why it works. Say you're given a function f of x equals ax to the n. Its derivative, according to the difference quotient, is a times x plus h to the n minus ax to the n all over h. Okay, well, if we factor out the a, and then we expand the binomial, x plus h to the n using the binomial theorem, we get that big mess right there in the third line. Well, if you focus on that, you see that the very first term is just x to the n. And when you subtract x to the n, that goes away. Now you'll notice that every other term in that expansion has an h as a factor. So you can pull the h out of the numerator and cancel it with the h in the denominator. Once the h in the denominator is canceled, we can let h go to 0. And since every term other than that first one there in the yellow box has an h in it, all the other terms will go to 0 as well. And that means the derivative will be nothing more than a times n choose 1 x to the n minus 1. And if you recall, n choose 1 is how many ways can you choose one thing from n things? That's just n. So a times n x to the n minus 1 simplifies to na x to the n minus 1. And that's the derivative of our power function. Now, the interesting thing to me about that proof is it uses the binomial theorem. And the binomial theorem we proved only for natural numbers. However, you'll find that the power rule works for any real number a and any real number n. So if you want to see why that is with a proof, you're going to have to wait until you learn a little bit more calculus. For now, you can rest assured that any power function, any real number a and any real number n, you could find the derivative using this rule. So now we can turn our attention to some really, really useful applications of the power rule. We'll start with a classic example. A ball is thrown up in the air, and its height in meters above ground is given by the equation h of t is equal to 1.2 plus 28.1 t minus 4.9 t squared. So time here is measured in seconds. That means the height of the ball is just simply some sad parabola. What we're asked to do is find h prime of t and explain its meaning. So finding the derivative is really as simple as finding the derivative of each of the three terms. First, we have 1.2. That's a constant. That means its exponent is 0, 1.2 t to the 0 power. So its derivative is 0. The next term, 28.1 times t, is raised to the first power. So its derivative will just be 28.1. So far, really simple. Last term is just as easy. Minus 4.9 t squared, its derivative will be 4.9 times 2, which is 9.8, and t to the first power, because you always decrease the power by 1 as you go through. Easy does it. That derivative, what it represents, is the rate of change of the height, also known as the velocity. It tells us how fast the ball is moving up and then back down. In part B, we're asked to determine the value of t when the derivative is equal to 0. That's as simple as setting h prime of t equal to 0, solving for time. When you do that, you'll find that the time is about 2.9 seconds. The significance of this time is really, really important. If the derivative is equal to 0, that means the velocity is equal to 0. What that means is the ball went up and then it came back down, and in between there was an instance when the velocity was 0. That is precisely the information that we need to answer part C, because the maximum height of the ball was achieved when the velocity was equal to 0 at its highest point. And so All I need to do is plug 2.9 seconds into my original function to work out that height. Be sure that you're plugging 2.9 back into the original function, not in the derivative. And that's because we want to find the height of the ball and not the velocity. When you plug it into the original function, you find that the maximum height is about 41.4 meters above the ground. Let's look at one more example. In this example, we're told that the total cost of running a train is given by C equals 2V times the square root of V plus 200,000 divided by V, where C is the cost in dollars and V is the speed of the train in kilometers per hour. The first part is just your standard function operation. What would it cost to run the train at 25 kilometers per hour? Okay, let's plug 25 in and see what the cost would be. You get $8,250. What about 100 kilometers per hour? I get $4,000. Quite a bit cheaper. Does this mean if I just keep increasing the speed, the cost keeps going down? Well, we'll have to investigate that. In part B, we're asked to find dc/dv and explain its meaning. Before I do, I have to explain this notation, dc/dv. It looks like a fraction, but it isn't a fraction. It is a rate. dc/dv is the rate of change of the cost with respect to the velocity of the train. That is, it's another way to express the derivative, c prime of v. The two notations mean the exact same thing. The advantage of the dc/dv notation is you can almost see the units on the derivative that you're calculating. dc means a change in cost, and dv means a change in the speed. So the derivative that I'm finding is representing how the cost is changing with respect to the speed of the train. Now, to find that derivative, we'll have a little work to do. Notice that my function is 2v times the square root of v plus 200,000 over v. That is a power function, but it doesn't quite look like it. Let's first start with the 2v root v part. 2 times v is 2 times v to the first power, and the square root of v is v to the 1/2 power. So if we add those exponents, we'll have v to the 3/2 power. Now that's written as a power function, 2v to the 3/2. The second piece, 200,000 divided by v, also doesn't look like a power function until you realize that a variable in the exponent, like the v is there, really just means a v to a -1 power. So when I rewrite c as a power function, it looks like 2v to the 3/2 plus 200,000 v to the -1. And that means I can find its derivative by taking 3/2 and multiplying it by 2 to get 3, and then decreasing the power by 1. 3/2 minus 1 gives me 1/2. For the second part, I'll take 200,000 multiplied by the exponent of -1 to get -200,000. And I will decrease the power of v by 1. Be careful here. If I take -1 and I subtract 1, I'll have -2. That is, my derivative is 3 times the square root of v minus 200,000 divided by v squared. In part C, I'm asked to find the speed at which the cost is a minimum. So what I need to do is use what I learned from the first problem. I can see from part A that the cost was decreasing, at least at some point, because it went from 8,000 down to 4,000. If it was increasing again at some point, then it would have reached a minimum. It must have. And that minimum could be found by setting the derivative equal to 0. When I set the derivative equal to 0 and solve for v, I have my speed at which the cost is a minimum. I'll spare you the messy algebra, but essentially, you just isolate the variable and use the standard techniques that you use to solve equations. You'll end up finding that v is equal to 200,000 divided by 3, all raised to the 2/5, which simplifies to 85. 85 what? Well, v was measured in kilometers per hour. I hope this video helps you understand what the power rule is and how it can be helpful in efficiently finding derivatives.